Okay, illustrative math, Algebra 2, Unit 4, Lesson 8 is called Unknown Exponents. All right, warm up. Solve each equation. Be prepared to explain your reasoning. So it doesn't really say how to solve it. Some of you might just plug in numbers till you get it right with trial and error. I'm going to use algebra here. I'm going to multiply each side by 3 here to get rid of the division. And here I get x equals 36. Let's see here. Before I square root both sides to get rid of the squared, I'm going to divide by 3. And that gives me x squared equals 4. And then I need to square root both sides. And remember, when I have to insert my own square root sign, I need to have a plus and minus. So I have actually two answers, 2 and -2. Cubed, I can cube root both sides. Or I want to also show you this. You could also do this. This came up the other day in a previous lesson. If I take it to the 1/3, this is the same. Okay, so you get the same answer. 3x cubed to the 1/3, you'd multiply those and you get 1. So this would be x equals cubed root of 12. You could leave it like that. You don't need a plus or minus when it's an odd root or an odd power, I guess. If you wanted to get a decimal, you could type it into your calculator. You could type either one, 12 to the 1/3 or the cubed root of 12. So I got 2.289. All right, this is better because it's exact. This is a decimal. All right, so this is the cubed root of x. So I need to cube both sides. So the cube gets rid of the cubed root. So that would be x equals 12 cubed is 1,728. All right, here's the pattern showing a trapezoid being successfully decomposed into 4 similar trapezoids at each step. If n is the step number, so these are my steps, this is my n. How many of the smallest trapezoids are there when n equals 4? Okay, so step 3, step 4, and then we want to eventually get to 10. So we might be able to kind of count here. There's, 1 trapezoid here. There's 4 here. If I count these up, I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we get 16. So you can see that it's really like times 4 times 4. Okay, so to get to this one, you could just, times it by 4 and then times it by 4, and you could get your answer right there. So, 16 times 4 would make this 64, and then times 4 again would give me 256. So the first one you can kind of like logically work your way there, but to get to the 10th one, let's see here. You're starting with 1, that's your initial value. So it's kind of like 1 times 4 to the x. That's step 1. It's like you multiplied by 1, 4. At step 2, it's like I multiplied by 4 and 4. So it's kind of like times 4 squared. Okay, so it's like I plug in a 2 there. So you can kind of figure out when it's 10, it would be, and I'm going to use t for trapezoids. Trapezoids equals 1 times 4 to the 10th. And I think that might be like kind of a giant number. No, my calculator can handle it, so I'll write it down. Thought it might be too big for the calculator. Let's see here. 1,048,576. So here's my function. At a certain step, there are 262,144 smallest trapezoids. So that goes into my function for t. And I really don't need the 1. Since it's 1, I'm just going to leave it as 4 to the x. So here's the problem. Your variable's in the exponent. We don't have a way to solve when the variable's up there in the power. Like when you look back here at all these ones we did here, I'll erase these. When you look at these, you don't have the variable in the exponent. We don't have, 2 to the x equals a number. We haven't done that yet. So these are called exponential equations when your variable's up there. So the only real way that we have is to kind of trial and error it. So, just start taking 4 and raising it to different powers and see what you get. 4 to the 5th is 1024. 4 to the 7th, 16,384. 4 to the 8th, 4 to the 9th. 4 to the 9th works, okay? So I just kind of just trial and errored. 4 to the 9th will give me what we're looking for. So the answer is 9, step 9. All right, write an equation to represent the relationship. So I kind of already did that. I said, they didn't tell me what to use for the variable. They just said write an equation. So I'll use t equals 1 times 4 to the n. And I don't really need 1 times anything. Explain to a partner how you might find the value of that step number. Just, I guess, plug the step number in for n. All right, so a lab colony of 100 bacteria is placed in a petri dish, or on a petri dish. The population triples every hour. Okay. How do you estimate the population of bacteria in 4 hours? So, again, you could kind of manually figure it out here. If, you start out with 100 and then every hour it triples. So this would be 0. This is 1 hour. I'm sorry, it shouldn't be 3,000. It should be 300. 2 hours. 3 hours. 4 hours. We end up right there. Okay. So you can kind of manually figure it out. It'd be better to come up with an equation and say population equals initial value, growth factors 3 to the h. Okay. Then you can plug in your hours there. Now, 90 minutes, you'd have to think how many hours is 90 minutes, and that would be 1.5 hours. Okay. If you wanted to change it to minutes, you could say population equals 100 times 3 to the minutes out of 60, because there's 60 minutes in an hour. So like if I plugged in 60, I would still get 3 to the first. And if I plugged in 1 for hours, 1 hour equals 60 minutes. So if I plugged 60 in here, I'd still get 100 times 3 to the first, which is 300, which I have right there. If I plugged in 1 here for h, because this is, if I want, these are equivalent, but I got to plug the hours into this function, I would get the same number. I get 300. So I'll just use the hours function. So it's 100 times 3 to the 1.5. So what's that give me? 500 and we'll call it 520. This just says hour. I don't know what that should say. That should say something else. Let me see what that says in your book. It looks like it should say half hour. So half hour, plug in 0.5 for H or 30 for M, either one. Should get the same answer. That gives me 173. How would you estimate or find the number of hours it would take the population to grow to 1,000 bacteria? So I plug in 1,000 for P, 100 times 3 to the H. So again, the only real way that we know how to do it right now is to trial and error. So I'm going to just start plugging in numbers. 100 times 3 to the, well, I know it's got to be between 2 and 3, right? Because I kind of already made a table here. So maybe try to the 2.1. 2.1, pretty close. So 2.1. How did I get that? I plugged in, I had 100 times 3 to the 2.1, and that gave me 1,005. Pretty close. Double the initial population. So I want to get to 200. So I want 200 to equal 100 times 3 to the H. So we know that it triples in 1 hour, it gets to 300, so it's probably somewhere between here. We know half an hour is 173, so maybe try like 0.6. 100 times 3 to the 0.6. It got me to 193. 100 times 3 to the 0.65. Pretty close. Maybe I can get a little closer. 100 times 3 to the 0.63. No. Gave me 189. 100 times 3 to the 0.64. That's pretty close. Okay. So I said H equals 0.64. And again, just trial and error. That's the only way we know. Okay. So this is kind of annoying. You're going to get tired of trial and erroring to find these exponent values. So we're gonna learn some methods here to solve these. All right, so let's complete the table. So here's my x. This is 2 to the x. So anything where we have the x, we could figure that out pretty easily. 2 to the 5th is 32, right? Because this is x. Here's my function. It'd be like 2 to the 5th. This would be 2 to the 1st, right? So that's 2. 2 to the 1/2. I'll just leave it like that. 2 to the 0. To the 0 is 1. Cool. So I got the easy ones. Backwards, though, we got to think here. 2 to what power gives me 4? So we got to start thinking, what would I raise 2 to get 4? Well, that's 2. This one here, 2 to what power gives me 16? So it's 2 times 2 times 2 times 2. You need 4 2's there. 2 to what power equals 256? 2 to the 7th, maybe? No. 2 to the 8th. There you go. And then the last one, 2 to what power equals 1024? Is it 10? 2 to the 10th? Yes. Okay, so a little bit of trial and error here. Ooh, this one, 2 to what power equals 1/4? Well, it's going to be -2 because 2 to the -2 is 1 over 2 squared, which would be 1/4. And then this one here, 2 to what power equals 1 over 32. Or wait, 2. So this is going to be -5. Kind of like the same thing here. It's 2 to the -5. Remember, a negative exponent flips it. 2 to the 5th is 32. So that's how I get the 1 out of 32. All right, next table. This time it's 5 to the x. So these are easy. These are just 5 to the 1/3. Rewrite that. That 5 looks like a 6. 5 to the 1/2. I can't, I could get a decimal, but I just leave them as exact. So again, here 5 to what power gives me 5? Well, that's 1. 5 to what power equals 125? That's 3. 5 to what power equals 625? That's 4. 5 to what power equals 3125? I think it's 5. 5 to the 5th, yeah. All right, 5 to what power gives me 1? That'd be 0, right? This would be 5 to what power gives me 1/5? Well, that would have to be a -1 to flip it, and this would be a -2. All right, how is finding the step number that would produce a certain number of trapezoids similar to finding the hours when a population reaches 1,000? How are they similar? I would say we are basically trying to find an unknown exponent, and we do not know any algebraic methods yet. So we have to trial and error, have to use trial and error to get close. All right, what are some ways to determine the exponent if we know the base and the value of the exponential expression? For example, if we know that 5 to the x has a value of 200, how do we find or estimate x? Trial and error numbers for x. It helps if we already have some values to get our guesses closer. All right, how is the process for solving an exponent like or unlike solving a variable in an equation 5x equals 200 or x to the 5th equals 200? How is it like or unlike? I mean, I would say it is like, because if we plug the solution back into the equation, both sides will equal each other. I would say it is different because we do not have a method to solve it yet. Okay, these ones we have a method. We divide by 5. We divide by 5. We take the 5th root. We take the 5th root. We don't have a method to do that yet. If I had like 5 to the x equals 200, I do not have a method to solve that. So that is why it's really different. All right, on the day a video was posted online, 5 people watched the video. So day 0, 5 people watch it. So views, days. The next day, the number of viewers had doubled, and so forth. Assume the number of viewers continues to double each day. On which day will 640 people see the video? Explain or show your reasoning. So your initial value is 5. You're multiplying by 2 every day. So we want that to be our function. We want to know when it will equal 640. So I'm just going to start plugging in numbers. 5 times 2 to the 8th. Too much. 5 times 2 to the 6th. 320. So it's between 6 and 8. 5 times 2 to the 7th, 640. So okay. What strategy would you use to find the first day when more than 20,000 people see the video if the trend continues? I would just probably continue guessing and checking. I would start with values greater than 7 because I know 7 gave me 640. Okay. All right. Thank you for watching this video for 4.8, and we'll see you on the next one.